After watching the following video, students are going to be able to calculate heat and specific heat values using the Q equals MC delta T equation. You're going to be able to calculate pressure, constant pressure calorimetry problems with appropriate assumptions, which will be pointed out during practice problems. You're going to be able to calculate your enthalpy from the calorimetry problems at constant pressure. And you'll be able to carry out constant volume calorimetry problems or calculations associated with bomb calorimeters. Calorimetry basically is a science or an observational procedure that allows us to measure heat flow from reactions or substances. And basically, that heat flow is correlated with the energy changes associated with that specific reaction type. And the instrument we use to make this analysis is called a calorimeter. And a calorimeter basically measures this heat flow, and it's a basic setup that you'll see. This is a constant pressure calorimeter. Notice you have a solution or water. You have a thermometer to keep track of the temperature changes when heat is released. You have a stir, and you have styrofoam cups and a lid. And the styrofoam cups and the lid are to contain the solution as well as insulate the reaction that's occurring so that heat or minimal heat leaves the reaction container. So we'll talk about the specific types of calorimetry. There's two main types, and we're going to look at also calculations associated with each and basically what they can each tell us. So let's go ahead and do that. So specific heat capacity, as we see written here as C sub S, is basically the amount of heat that a substance can absorb that will actually raise the temperature of 1 gram of that substance by 1 degree Celsius. So different substances have different specific heat capacities. Notice aluminum requires 0.9 joules of energy in order to raise 1 gram of aluminum's temperature by 1 degree C. If you look at water, it also has a very high specific heat capacity, actually the highest of the bunch. So it requires, almost or slightly over 4 times the amount of joules of energy to raise its temperature by 1 degree C. So in terms of the ability for something to change temperature, you can look specifically and compare two different substances. So let's pretend we had a bike made of aluminum and a bike made of iron. Okay, and we both if we left them in the sun, went inside, had lunch, and came back out on a hot day. Now, the specific heat capacity of aluminum says that it takes 0.9 joules to raise the temperature of 1 gram by 1 degree C. Iron is approximately half of that. So when we walk out, the iron frame, theoretically at least, should have absorbed more energy or should have absorbed enough energy to change its temperature of the frame a lot more than the aluminum frame. So we can look at heat capacity in a more generic way. Just heat capacity in general of a substance is the amount of heat required to raise a temperature of any given quantity in terms of mass or moles. It could be really anything of the substance by 1 degree Celsius. So you could use moles here, you could use 100 grams, you could use various different things. However, typically when we're looking at specific heat capacities, we're looking at it with respect to 1 gram. It's specific. This is a more generic approach, but it's the same thought process. Now, we're looking at the heat that's being absorbed by substances or heat that's being released by substances. And because we're looking at that Q, we're able to look at the relationship of Q with the components of specific heat. So Q is going to be equal to your mass, right? So in this case, specific heat, remember, relates 1 gram and 1 degree Celsius. So we have our mass, we have our specific heat capacity, and we can also look at our change in temperature. These will all allow us to interrelate these components from our specific heat definition to find what Q actually is. And remember, delta T is your temperature final minus your temperature initial. And this equation will play an important role in calorimetry problems, especially constant pressure calorimetry. So let's go ahead and look at a couple problems. So how much heat is given off when an 869 gram iron bar cools from 94 degrees to 5 degrees C? Okay, well, in this case, we know that we're going to be using the Q equals mc delta T equation because we've been given our mass, we've been given our information for delta T, we've been given the identity of our substance, and so Q is the thing that they're wanting us to solve for, and so that equation is what makes the most sense. So what are we going to need to do? Well, first things first is we have our substance, which is iron. We need to look up its specific heat capacity. So we would look up on the table, like the one we saw in our last slide, and we'd find out the specific heat capacity. Remember, the iron value was 0.44 joules per gram degree Celsius. So we have that here. We got that from the chart. Now, we can also look at our delta T by looking at our changes in temperature. Now, we went from 94 degrees C to 5 degrees C. So our initial is 94, our final is 5, right? So we go from our friend's house to school, right? So our initial value is going to be the 94, our final value is going to be 5 degrees C. So when we plug that into this equation, we get 5 degrees C minus 94. That gives us negative 89 degrees C. So obviously we've decreased our temperature. And then what we do is we plug in these values into our equation here. So 869 grams, so that's our M value, 0.44 joules per gram degree Celsius. That's our specific heat capacity, C sub S. And we plug in our negative 89 right here. Okay, we multiply all of that together, and that gives us negative 34,000. If we do a unit evaluations, grams and grams cancel, degrees Celsius and degrees Celsius cancel, joules are what's left over. So, from that 869 gram bar of iron, when it changes this drastically, it's giving off this much heat as it cools. So we have a very similar problem here. We've been told that a 6.22 kilogram piece of copper metal is heated from 20.5 degrees C to 324.3 degrees C. And they want us to calculate the heat absorbed by the metal. Okay, so obviously we've gone from a lower temperature to a higher temperature, so some absorption has occurred. So if we go ahead and we look at the pieces that they've given us our mass, okay, 6.22 kilograms. Now we know that our heat capacity for copper, if we look it up on the table, is going to be 0.385 joules per gram degree Celsius, and our delta T is going to be equal to 324.3 minus 20.5 degrees C. Now, something I want to point out is that our units need to match in terms of all of these variables in order to solve for Q, because obviously you have to have units cancel. So we have degrees Celsius, joules obviously is the standalone, but kilograms and grams do not match. So before we plug these numbers into the Q equals mc delta T equation, we need to make sure that all of the units are matching. So in this case, we need to take kilojoules and convert it into, kilograms and convert it into grams. So, we're just going to move our decimal to the right a few spaces, and this will give us the correct unit. Then we're going to take all these numbers and plug them in as we see here. Basically multiply everything through, and that should give you, 728,000 joules. Grams and grams cancel, Celsius and Celsius cancel, joules are left over. If they want the units in kilojoules, you just go from joules to kilojoules by moving the decimal to the left 3 spaces, as you guys are familiar with. These types of problems, just make sure that you're paying attention to the units. Make sure that you're utilizing the correct specific heat capacity for the specific substance that you've been told that you're dealing with, and all should be right. You can also solve for other variables. If they gave you Q, and they gave you delta T, and they gave you specific heat, you could also solve for the mass of the substance. Basically, as long as they give you 3 variables, you should be able to solve for the remaining variable. So let's go ahead and look at one of those examples where we're solving for something other than heat. So they've told us that we have 250 joules of energy absorbed by a specific sample. They've told us the mass of that sample. They told us the identity of the sample. And they told us the initial temperature of that sample. Now, they want us to calculate the final temperature of the gold. Okay, now if we look at this specific equation, notice that there's no temperature final or temperature initial. So basically, we're going to have to take 2 steps in order to calculate for temperature final. However, we do know that if we solve for delta T, we can get close to our temperature final information. So what are we going to do first? First, we're going to figure out all the variables. They gave us Q, which they told us we have 250 joules. They told us our mass, which is 45.0 grams. They told us what our substance is, so we can look up the specific heat capacity of gold on the chart that has specific heat capacities. All of our units here match, okay? And the only thing that we don't have from this equation here is delta T. So we can plug in all 3 of these variables and solve for delta T. So if we go ahead and do that, this is what it looks like, right? We manipulate the equation. We're going to divide out the 45 grams times 0.129 joules per gram degree Celsius. We're going to divide that into the 250 joules, and that's going to give us a delta T of 43.1 degrees Celsius. Now, they are not asking for change in temperature. They've asked us to calculate the final temperature. So remember that delta T is equal to temperature final minus temperature initial. So if we want to know what the temperature final is, we're going to need to manipulate this equation. So that ends up looking like temperature final is equal to temperature initial plus your change in temperature. So we know that your delta T is going to be plugged into here. We've been told our temperature initial. All right, they told us that the piece of gold was 25 degrees C initially. So we plug these in appropriately. And our temperature final is 68.1 degrees C. The original question or the original statement told us that energy is absorbed. So an increase in temperature and our temperature final value makes a ton of sense. Constant pressure calorimetry takes advantage of the apparatus that we see here on the left. We described the details of it earlier. So basically, remember you have a solution here. Either you're mixing 2 solutions to measure a reaction, or you may take a solid of some sort that's been heated and put it into, just pure water and measure those values. And we'll look at how that applies here in a little bit. But basically, constant pressure calorimetry, the reaction is carried out at constant pressure. We're not expecting any changes there because the reactions are confined to either the solution phase or 2 phases that aren't going to release any products that would change the pressure. So because the reaction is at constant pressure, we can use the relationship between heat and enthalpy. So your change in enthalpy is going to be directly related to the heat either absorbed or released by the reaction that you're studying. We are going to be using the equation Q equals mc delta T in order to do some of our calculations. And actually, we're going to be observing the solution and the changes that occur in the solution in order to determine our heat released or absorbed by our reaction. So basically, we're kind of indirectly monitoring the reaction and utilizing this relationship and the Q equals mc delta T equation in order to find out information about that reaction. So it's a very straightforward process. It's obviously not, you're not going to be getting values that are going to be tabulated in the back of a chemistry book, but you're getting pretty accurate information for the most part. So let's take this calorimetry problem. They've told us that when a 4.25 gram sample of solid ammonium nitrate is dissolved in 60 grams of water, that's inside a coffee cup calorimeter, the temperature drops from 22 to 16 degrees C. They want us to calculate the change in enthalpy in kilojoules per mole of the ammonium nitrate, and they've told us to assume that the specific heat of the solution is the same as water. So what we're going to be able to directly measure is the changes that are associated with the solution in the calorimeter. All right, so Q of our solution is going to be able to be calculated directly from the information that we have been provided. So they've given us information to calculate the mass of the solution. They've told us some assumptions about the solution, and of course we can calculate our delta T. So the M of our solution, okay, is going to be equal to the sum of the components of said solution. So we know we have 4.25 grams of our ammonium nitrate, and we have 60 grams of water. Okay, so that's going to give us 64.25 grams of our solution. Okay, they told us that the specific heat of our solution should be assumed to be the same as pure water, so we're going to plug in our 4.184 joules per gram degree Celsius. Okay, and of course our delta T of our solution is going to be calculated by taking the difference between the final and initial temperatures. So our final temperature is 16 degrees and our initial temperature is 22, so 16 minus 22, okay, that's going to give us negative 6.0 degrees C. Now a couple things to notice in this problem. Okay, we have considered the mass of the solution to be the sum of all the total parts of the solution here. They've provided us with mass values so we can easily make this calculation. Okay, in terms of assuming that the solution has the same specific heat capacity of water, this will occur very regularly in calorimetry problems because, you know, the solution that's inside the container is typically mostly water anyway. Okay, and of course the delta T calculation is the same as other calculations you've done. So now let's go ahead and calculate our Q of our solution. Okay, so Q of solution is going to be equal to 64.25 grams, which is the mass of our solution, times our specific heat of our solution, multiplied by our change in temperature. And that's going to be equal to the following value. Okay. We follow that with a unit evaluation. Grams and grams cancel, Celsius and Celsius cancel, and joules are what we're left over with. Okay, so what we've calculated here is the change in the solution when the dissolving of an ammonium nitrate occurs in water. Now, I want to know the change in enthalpy associated with the ammonium nitrate. So really what I'm trying to find out is the Q of the reaction, or the Q of the dissolving process for the ammonium nitrate. And we know, based on what we've discussed before, that the negative Q of your reaction is equal to the Q of solution. We directly measure Q of solution so that we can indirectly determine the Q of our reaction. Okay, so since I know that my Q of solution is equal to the following, okay, I can indirectly figure out my Q of reaction. Okay, so Q of reaction in this case is obviously going to have equal value but opposite sign of our Q of solution. So Q of reaction is now corresponding directly to the dissolving process of the solid ammonium nitrate in the water. Now, because we are carrying this out in a constant pressure setup, we know that delta H, or change in enthalpy value, is equal to the Q of reaction. So since I know my Q of reaction, I by default know the delta H value. So delta H is equal to the following value. Okay, now
they want us to express our delta H in kilojoules per mole of ammonium nitrate. So the way that we're going to calculate that is obviously we are going to convert our delta H value into kilojoules, and then we're going to divide that value by the total number of moles of my ammonium nitrate. So let's go ahead and convert our joules into kilojoules. So we know that there's 1,000 joules for every 1 kilojoule. Okay, so that gives us 1.612 kilojoules, okay, for our delta H value. And now we want this per mole of ammonium nitrate. So 4.25 grams of our ammonium nitrate is going to be converted into moles of ammonium nitrate, as follows, which equals 0.05309 moles of ammonium nitrate. Okay, and we're going to take that value now and we're going to divide our delta H in kilojoules by this molar amount. And that's going to give us 30 kilojoules per mole of ammonium nitrate as our final answer. So we have another calorimetry problem here. In this case, they've told us that we've mixed 50 mils of 1 molar HCl and 50 mils of 1 molar NaOH into a coffee cup calorimeter. When we mix these two solutions, the temperature changes from 21 degrees C to 27.5 degrees C. They want us to calculate the Q of the reaction. They want us to calculate the enthalpy value. And they want us to calculate the enthalpy value per mole of HCl for this specific reaction. Okay, so once again, guys, this is a calorimetry problem. So of course, we are going to be indirectly measuring the interaction between this HCl and NaOH. Okay, so HCl and NaOH, we know that when we put them together, because they're an acid and a base, we know that we get neutralization. So H2O and NaCl are the products that we would produce. And because this is a calorimetry problem, we know we're going to be looking at the Q of the solution directly so that we can indirectly measure our Q of reaction. So our Q of our solution is what we're going to be calculating initially in order to figure out our Q of reaction. Now, there's a few assumptions we're making here, just like we have in other problems. Okay, so first of all, guys, we are assuming that the 50 mils of each of the reactants is going to basically sum to a total volume of 100 milliliters. Okay, so we have 100 milliliters because 50 and 50 give us 100 mils. Now, we are also going to assume that the mass associated with these two solutions is going to basically be having the same density as water. Okay, so the volume of our solution, we're going to assume that its density is the same as water, okay, which is 1 gram for every 1 milliliter. Okay, and so basically what we're assuming is that the density of the solution is the same as the density of water, because these two are basically primarily made up of water, and that's going to allow us to get our mass of our solution. Okay. In that same vein, we're also going to assume that our specific heat capacity of the solution is the same as the specific heat capacity of our water, just like we've assumed in the past. Okay, and that's going to allow us to calculate our Q of our solution. Okay, so we have 100 grams of our solution times our specific heat capacity of our water. Okay, and of course we need our change in temperature, which is calculated by taking our final value of our temperature of our container minus our initial, okay, which is equal to 6.5 degrees C. We'll plug that in, 6.5. Okay, we're going to go ahead and multiply this out, That's going to go ahead and give us 2719.6. Okay, units wise, grams and grams cancel, Celsius and Celsius cancel, joules are what we've obtained. Okay, so that is our Q of our solution. Okay, so now if we want to find our Q of reaction, we're going to go ahead and change the sign of our Q of solution, which is subsequently going to give us the following value. Now this is our Q of our reaction, so the heat associated with the process of HCl and NaOH interacting with one another. So now we want to find our enthalpy value. And remember, because this is a constant pressure situation, our enthalpy value is equal to our Q of reaction. Okay, so this is our corresponding enthalpy value. The last thing they've asked us to calculate is the enthalpy per mole of HCl for this reaction. They have not specified what units the enthalpy need to be in, so I'm just going to leave them in the joules as they are here. So much like we've done, we first need to figure out our moles of HCl. Okay, so basically if we take our 1.0 molar concentration of HCl, okay, and we multiply it by our volume in liters, the conversion of which looks like this. We have 1,000 milliliters for every 1 liter. Okay, this is going to give us 0.05 moles of HCl. And then now we can find our enthalpy per mole of HCl by taking our enthalpy value and dividing it by our moles of HCl. And that's going to give us the following value. In this calorimetry problem that we have here, we're taking a solid sample and heating it, and then we're going to add that solid sample into a calorimeter containing water. In this context, we are dealing with a solid that's not going to dissolve in solution, so we do not sum the total masses of the sample that's added to the water that's in the calorimeter. Okay, so in this situation, the Q of our solution is going to actually be Q of our water, because we're actually measuring the mass of the water directly, the temperature of the water directly, and that's going to allow us to figure out the Q of the reaction, or in this case, the Q of the solid. Okay, so this is the relationship that we're going to use, and basically the approach that we're going to take is to find the variables of the known, which is the water, to help us find an unknown value, which is the specific heat capacity of the solid. So we're going to calculate the Q of our H2O, okay, and we're going to plug in the mass of our water, okay, times the specific heat capacity of our water, times the change in temperature of our water, which goes from 25.10 degrees C to 28.49. So that's our final temperature minus our initial. Okay, and this is going to allow us to figure out the Q of H2O, which is equal to 709.188. Okay, and unit evaluation is going to leave us with joules. So this is the Q value associated with H2O. So this is what we've measured directly. Now this is going to allow us to figure out the Q of the solid indirectly by using the relationship we see here. Okay, so Q of solid is going to be equal to the Q of the H2O, but just with the opposite sign. So this is our Q of our solid. Now, they don't want the Q of the solid. What they want is the specific heat capacity. So they want the C variable. So Q of our solid is equal to the mass of our solid times the specific heat capacity of our solid times the change in temperature of our solid. So the variables that I'm able to determine, obviously I know Q, they've provided us with our mass, okay, and delta T can be calculated from the information provided above. So the Q of our solid is provided here, okay, the mass of our solid is 25.64 grams, as it says in the problem above. Okay, our C of our solid is what we don't know, we're trying to figure out. Okay, and our change in temperature of our solid can be calculated from the information provided. Okay, so we know that the initial temperature of our solid is 100 degrees C. Okay, and we know that the final temperature of the solid is the same as the final temperature of the water inside the calorimeter. So 28.49. So final 28.49 minus 100 degrees C gives us negative 71.51 degrees C as our change in temperature for our solid. Now, if we go ahead and we manipulate the equation here, we can get C solid all by itself. So our specific heat capacity of our solid is going to equal the Q of our solid divided by the mass of the solid times the delta T of the solid. Okay, and we can go ahead and plug in our variables. Okay, so C of our solid is going to equal negative 709.18 joules divided by the mass of our solid, which is 25.64 grams, times negative 71.51 degrees Celsius. Okay, and we go ahead and plug those into our calculator. That's going to give us a specific heat capacity of 0.387 joules per gram degree Celsius. Okay, and that's the specific heat of the solid that we used in this calorimetry problem.
So now we're looking at constant volume calorimetry. So in constant volume calorimetry, the reaction is being carried out at a constant volume. So no pressure volume work can actually be done because there's no change in volume. So because of this, the value that we're actually calculating or analyzing is not enthalpy. We're going to be looking at delta E. So in this case, delta E is equal to the heat from the reaction. Now, in constant volume calorimetry, this is obviously much more precise, much more accurate, and so the information obtained here is what actually usually ends up in textbooks and things like that, in the appendices of the textbooks. So if we look at the constant volume calorimeter, you notice that it looks somewhat similar. There's some water, there's a thermometer, there's a stir, okay, there's some similarities. The water, the temperature changes associated with that is what we're using to track the change in that calorimeter. The stir, once again, is used in the same way, but notice that there is kind of a container inside the calorimeter. Okay, so what we do is we put a sample, a chemical, inside this sample cup. We ignite it, and then we directly measure the heat flow that occurs into the solution and the surrounding calorimeter. So I want you to notice that the C-cal here, this represents the specific heat of this specific calorimeter. So it includes the water, and it includes all of the heat potentially absorbed by the calorimeter that's surrounding. So we haven't considered that in the constant pressure calorimetry problems. We've assumed that it's minimal. In this situation, we're trying to get very, very accurate numbers. So the calculations and the values associated here are very specific, and they're associated directly with the calorimeter that you're using. So in this case, the calculations are a lot more straightforward. All you do is put the sample in. The C-cal has already been calculated for the instrument, so whatever heat is being released, it'll be directly tied to the calorimeter change, or sorry, the calorimeter specific heat capacity and the delta T. So knowing the difference between what kind of calorimetry is occurring, you're either going to be told you're using a constant volume calorimeter, or sometimes they're called bomb calorimeters because they're closed up systems. If you're told that, then you definitely know that this is the equation that you're going to be using. Sometimes you're not told, so you need to look at what you've been given, and we'll look at that in a few slides. Okay, so let's go ahead and let's look at this example. 500 grams of fuel, 500 gram fuel samples burned in a constant volume bomb calorimeter. Okay, so they've told you that you're using the constant bomb calorimeter, so you know that you're going to be utilizing this type of equation. This bomb calorimeter has a heat capacity as follows, and the temperature of the bomb calorimeter when we burn these 5 grams of fuel is 3.25 degrees C. So they could have asked this in several different ways. They could have totally left out constant volume bomb calorimeter, and they could have said, 5 gram fuel sample is burned in a calorimeter that has a heat capacity of this. Okay, so notice the units here are different for our heat capacity, and notice they would have told you that the calorimeter has this heat capacity. Remember that this C value here is for the calorimeter, so for the instruments that's being used to run this reaction. So even if they don't tell you it's a constant volume or a bomb calorimeter, you can get the hint based on the units associated with the calorimeter, them telling you that the specific heat capacity of the calorimeter is as such, etc. All right, so now that we kind of understand that, let's go ahead and let's look at what they want us to actually figure out. So they want us to calculate the heat given off by the sample in kilojoules per gram. Okay, so our heat of our reaction is going to be calculated in a very similar way that we've been doing. We're just going to plug in our specific heat capacity and our change in temperature, which we've been given both of those. We multiply those out. It gives us this answer, so negative 8,160 joules, right? Celsius and Celsius cancels. Okay, those units cancel, so joules are what's left over. Now they want us to calculate the heat given off in kilojoules per gram. So obviously we're going to take our joules and convert them into kilojoules. So pretty straightforward there. Okay, now they're then wanting us to calculate the heat given off for this reaction. So this is a heat of combustion because we've combusted a fuel. But they want us to calculate this based on kilojoules and grams. So we know that our Q value is equal to, should be negative 8.16 kilojoules. Okay, and we're going to divide out by our mass, which is 5.00 grams. Okay, and that will give us this answer here. Okay, so our heat of combustion, when we combust this sample, when we burn this sample, we get negative 1.63 kilojoules for every gram that is burned. So the bomb calorimetry calculations are really nice because you don't really have to pay attention to all the little details like you do with the constant volume calorimetry or constant pressure calorimetry. But, obviously you're still going to be looking at units, you're still going to be looking at what the sample is, etc. So just make sure you're paying attention to what type of calorimetry based on the units that you have or based on how the question is actually worded. And if you follow those steps, you'll be fine.